Okay, still working with the t-statistic, but this time they gave us actual data. So we're going to take a look at this. A city health department wishes to determine if the mean bacterial count per unit volume of water at a lake beach is less than 200. A researcher collected 10 water samples of unit volume and found that the bacteria count to be, and it has these different levels of bacteria. You may assume that the measurements constitute a simple sample from a normal distribution. That is really critical. We cannot use the t unless the underlying distribution is normal or we have a sample size greater than 30 or larger. We only have a sample size of 10, so we need to know that the underlying population is normal, or we're going to have to draw a box plot to check out our sample to see if it indicates that it is symmetric at least. So we want to know, they're telling us it needs to be 200, so we're going to go ahead and assume the claim is it's 200. So I'm going to go ahead and enter that information into stat edit. So stat edit, I type in the information, then I'm going to go stat calc, one variable statistics. My list should be L1. I should not have a frequency because there's only one value. And I find out that X bar is 194.8, and the standard deviation of my sample, and we know it's standard deviation of sample because these were our actual measurements that we took, it's not from the population, is 13.13, and we'll just call it 13.14, and that'll be good enough. All right, my sample size is 10, so N is 10, which means my degrees of freedom are 10 minus 1, which equals 9. Very important that you show that. All right, so since we're working with the standard deviation of the sample, we're working with a t-statistic. Once again, our formula for a t-statistic is t equals x bar minus mu s divided by square root of n. Okay, now the question is, which way are we shading? Well, the claim is that is 200, and we want to make sure that we're extreme or more extreme from that, which in this case would be 194.8 or less, because we are hoping for a little bit, we're hoping for clean water to be drinking, so we're hoping that it's less than 200. So we have the probability that t is less than or equal to, or you can just use the less than symbol, 194.8 minus 200 over our standard deviation of 13.14 divided by our square root of our sample size, which happens to be 10. Now, when we go through the math, we end up calculating a fairly large t-statistic. And so we're looking for the probability that t is less than or equal to 0.252, a negative 1.252. All right, and that's if I calculate that by hand. So going to the calculator, stat, we're going to go second vars, and once again we need to be able to do this both ways, and I'm going to do this both ways. Second vars TCDF, our lower bound this time, we're going to negative infinity. Our upper bound is negative 1.252. Our degrees of freedom are 9. Be careful about that. Don't make a simple error there. And we end up getting a probability equal to 0.1211. And that's our probability that it's going to be, that we would get a sample as extreme or more extreme given that it was 200. So that's our answer, 0.211. Now, probably the faster way, stat, test, t-test, but this time we're not using statistics, we're actually using real data And the calculator is pretty smart. We still have to put in our mean. Our mean claim was 200, but my data list is an L1, so second one for my data list. Now, we shaded to the left and we used a less than symbol, so we need a less than symbol here. And there we go. There's my t-statistic of negative 1.252. There's my probability of 0.121. There's my sample mean of 194.8 and my standard deviation of 13.14. Please remember, this may be the fast method, but you are going to be required to use t-statistics, the second VAERS t-statistic as well, to calculate these answers. So once again, that's what our work should look like. Thank you.